As we move into early 2026, state-sponsored hackers are actively intercepting and siphoning massive streams of encrypted global data into dark, inaccessible vaults. They cannot read this information today. Instead, they are executing Harvest Now, Decrypt Later attacks, stockpiling financial records and state secrets while waiting for the hardware to catch up to the math. This is the hardware they are waiting for. The arrival of a functional, large-scale quantum computer marks Q-Day, the moment current public key cryptography becomes obsolete, as quantum algorithms solve prime factorization problems in hours. This is the second quantum revolution. It is a trillion-dollar era defined by fault-tolerant computation, room-temperature quantum batteries, and unhackable photonic networks. To understand how engineers are building this landscape in 2026, we have to look back a century to the moment physics appeared to reach a dead end. The security of our global infrastructure now rests on a discovery made when the classical laws of reality failed to explain the behavior of a heated object. In the late 19th century, Newtonian mechanics and Maxwell's electromagnetism were the final authority on how the universe operated. This graph highlights the ultraviolet catastrophe. Classical math predicted that heated objects would emit an infinite amount of energy at high frequencies, but experimental data showed a stable, peaking bell curve. In 1900, Max Planck set out to bridge this gap between theory and data. Planck discovered that the only way to match the data was to assume energy is not a continuous stream, but instead arrives in discrete, indivisible packets called quanta. This mathematical artifice solved the blackbody problem, but it also proved that reality at the subatomic scale is not smooth, it is discrete. By the 1920s, a new generation of physicists began building a rigorous framework for this discrete reality. Werner Heisenberg developed matrix mechanics by focusing only on observable data, discarding visual models of electron orbits that no experiment could actually see. Erwin Schrödinger took a different path, derising a wave equation that described subatomic particles as probability distributions. This led to the concept of superposition, the rule that a quantum system occupies all possible states simultaneously until a measurement forces a single outcome. Paul Dirac then unified these ideas with special relativity. His equations required the existence of antimatter, a prediction that was experimentally confirmed just 4 years later. This first quantum revolution allowed us to utilize the collective behavior of quantum particles. By applying these rules to the bulk effects of matter, engineers built the transistors, lasers, and MRI machines that power the current digital economy. But while we could use these collective effects, we lacked the tools to isolate and control the individual quantum pieces. Today, the industry is transitioning from observing bulk phenomena to actively isolating and engineering individual quantum states, known as qubits. The primary obstacle is decoherence. Because qubits are extremely fragile, minute environmental interactions, like thermal noise or electromagnetic interference, destroy the quantum information. To solve this, Google and ETH Zurich achieved a 2026 milestone, crossing the threshold into below-threshold error correction. They proved that by grouping physical qubits into a shielded logical qubit, adding more hardware actually reduces the error rate. This allows for lattice surgery, the ability to isolate and fix errors during active calculations without pausing the system or destroying the delicate quantum state. As of 2026, these hardware breakthroughs have moved quantum computing from theoretical physics into a scalable commercial engineering race. The theoretical blueprints from the 1920s are currently reshaping hardware in energy storage and high-speed communications. In March 2026, researchers at CSIRO demonstrated a proof-of-concept quantum battery. It utilizes a collective effect called superabsorption to charge via laser light. This chart shows the property of super-extensive scaling. Unlike a chemical battery, the quantum battery's efficiency increases and its charge time decreases as its physical size scales up. This same mastery over quantum states has revealed 48-dimensional light. By manipulating the orbital angular momentum of photons, researchers are creating a data alphabet robust enough for noise-resistant quantum networks. To counter the threat of Harvest Now, Decrypt Later attacks, firms are already deploying chip-scale quantum key distribution. These circuits use physical quantum states to secure the grid against future decryption attempts. The century-long journey from Planck's quanta to 2026 hardware shows that true technological leaps come from discarding classical assumptions and rewriting the rules of reality from the ground up.